Over the past few videos, we have been looking at differentiation of vector-valued functions of multiple variables. And one of the key objects that we have defined and used is the Jacobian matrix. In this video, what we're going to start is our exploration of higher level differentiation. So that is going to lead us to something called the Hessian matrix. My plan in this video is to explain to you how to compute the Hessian matrix. This is something I sometimes see done incorrectly in, say, random sources on the internet. So I will take you through the proper derivation of the Hessian matrix. We'll look at a very quick, very simple example just to make sure we understand the notation and all of the subscripts that I wrote down when we talk about the Hessian matrix. After that example, I will wrap up with a discussion of what kind of operator the Hessian matrix is. So it's going to be a matrix, and it's like a matrix, we think of it as acting on something. So what does the Hessian matrix naturally act on? And as we discuss that, we will come up with another interpretation for exactly what the Hessian matrix is, so a way for you to think about it. Okay, so let me back up a bit first. In this particular discussion, we are only going to focus on scalar-valued functions of, say, n variables. So throughout this lesson, we will imagine that the function f is a twice differentiable function on some open domain A, which is a subset of Rn, but it sends us to scalar values. That's not a bad assumption because this kind of function is very practical. For example, if you are measuring a quantity in space, that could be a scalar valued function of 3 variables. The main reason that we will make this assumption is in part dimensionally motivated. So I will mention when we get to the form of the Hessian what we would have to be thinking about if we were looking at, say, a vector valued function of n variables. So we'll say, in a different class, we might explore this, but in this particular class, we're going to stick with things that we can easily write down. All right, before we talk about the Hessian, I just want to make sure that we are all on the same page as far as notation goes. So I imagine that you've taken multivariable calculus and you're familiar with the idea of differentiation with respect to one variable and then the other. I often, to save space, like this subscript notation. So this means the derivative of df dx with respect to y. So first differentiate the function f with respect to x, and then with respect to y. So I like this, but if you prefer Leibniz notation, of course, this is the translation of that exact idea into Leibniz notation. Notice the different order in the denominator, or what looks like a denominator here, and that's because we imagine this differential operator kind of acting from the left. So the appropriate way to say differentiate with respect to x and then with respect to y is to write x and then y kind of right to left. Okay, so again, I imagine that you've seen this notion before. I just want to make sure that we all write down this idea of a second partial derivative the same way. I also want to mention Clairaut's theorem. This is another concept that I think you would have learned in multivariable calculus. I will just state this here. For all of the functions that we look at in our study of real analysis 2, Clairaut's theorem will hold. Meaning that if I'm talking about second order differentiation, the function f in question is class C2. C2 means that first and second partial derivatives not only exist, but are continuous. So in other words, the second partial derivatives that will emerge from this kind of computation look like nice functions in their own right. If that's the case, Clairaut's theorem tells us that differentiating with respect to x and then y is the same thing as differentiating with respect to y and then x. So in other words, order doesn't matter. F sub xy would be the same thing as f sub yx. I just want to state Clairaut's theorem here. I don't want to kind of change topics and start proving this, but if you're interested, I will have a different video where I just take you through the proof of Clairaut's theorem. It's, in my opinion, kind of an interesting proof geometrically. So if you sketch out, what we're going to do in that proof, I think it's a nice geometric exercise. It's also a proof which is incorrect all over the internet, and I'll talk about that in that video. Okay, let me now set up what we will need in order to discuss the Hessian matrix. All right, let's work through what will turn into the derivation of the Hessian matrix for this twice differentiable scalar valued function of n variables. So we imagine that f is twice differentiable. That's a concept that you would have seen in single variable calculus. So what does it mean for a function of the form y equals f of x? It means you can do f prime prime. What are you doing when you do f prime prime? You're doing f prime of x prime, right? So you're differentiating the first derivative. We want to now grow this idea into the type of function that we are studying in this lesson, so scalar-valued functions of n variables. We know that when we do, say, the first order differential operator, that's this Jacobian matrix that we've written down now several times. So now we want to say, well, what would it look like to evaluate the derivative of this? Okay, I've written this down as if it's being evaluated at some specific point P. So maybe for a given choice of P, this is a matrix of numbers. That's not what we want to consider. So imagine that df of x is differentiable with respect to this point. So it's like with respect to the input x, the choice of point from the domain A. This is going to be a new way of thinking about the Jacobian because in the past, I've always said, treat this like the name of a linear transformation. So the fact that it's like df parentheses at some input p, this is really just a funny way of naming an associated linear transformation. We're now going to break this off and imagine what it would look like to compute the rate of change of this expression with respect to the input from the domain A. Okay, so that's one thing we have to consider. And let me write down the difficulty here, or what we need to account for. Okay, I'm going to write down some functions, what domain they map from and the codomain they map to, and then I'm going to say how they send points from the domain. So the first one is f. We know that this is a twice differentiable map from some open subset of Rn to R because we're only looking at scalar valued functions. What does it do? Well, it takes a point P from Rn and maps it to f of P, which is a scalar. So this is a function from vectors to scalars. Okay, that's not too surprising. What about this idea of df? Again, I'm breaking off the first part of this name of the linear transformation. So df, well, we evaluate df at P, so it's also going to have the same domain as f. We'll think of it as a map on the open set A, which is a subset of Rn. Before I write down what's going on over here, let me proceed to the second line. It will take P and send it to df at P. For this particular context of looking at a scalar valued function of n variables, this object is a 1 by n row matrix. In the general language, if f were vector valued, say f was a map from A subset Rn to Rm, this would be an m by n matrix. We would think of it as a linear transformation. So df, this idea of like building up a Jacobian matrix on different points of A, this takes points of A and sends them to linear transformations. We can write that as this notation. So this is a linear transformation from Rn, sending us to scalars. In the general language, you could use Rn, Rm here, but what I'm trying to say, if you want to forget the notation, that's fine. This is linear transformations. df is not scalar valued. It is not vector valued. It's like linear transformation valued. That is not the kind of function that we have built up a robust theory of differentiation for. So if I want to proceed, I have to think like, how can we justify what it would look like to essentially compute like a Jacobian matrix for this operator, given that it does not have the form of the maps that we have been looking at? So what we will recognize is that there's a very closely associated object for this Jacobian matrix. And for a scalar valued function, that is the gradient. Okay, the gradient of f, you can think of it as the transpose of this row, so it's a column. But what that means is, again, it's going to start with the same domain. If I do the gradient of f and then I evaluate it at P, what kind of object do I get? It might seem pedantic, but there's a distinction here. So this is a linear transformation. That's the natural interpretation. This is actually a vector in Rn. So this is vector valued. So this is the kind of function that we already know how to differentiate. Here's what we're going to do. Since this is a vector-valued function on n inputs, we will use the regular approach to compute the Jacobian of the gradient of f. Then we will just transpose the result, since the gradient of f is the transpose of the original Jacobian. So we'll compute capital D of the gradient of f, transpose it, and say that's d of df. If you're wondering if that's fair, like why can't I just transpose it and know that I've done the right thing? Keep in mind what the active differentiation is doing. It's measuring rates of change. So we want to write down something that reflects how this object changes as a function of the point x in the domain where we're computing the total derivative. Since the pieces of this Jacobian matrix, or Jacobian row as it is in this particular context, since these pieces are all the same as these, if we can detect how the coordinates of the gradient change with respect to the input, that's going to give us the same rates of change. It's basically just arranged differently. So it feels like I'm being pedantic, but what I want to emphasize here is that you really must think dimensionally about the objects that you're computing with. So in real analysis, always know, what kind of space you're working in. The Jacobian matrix here doesn't send us to the same kinds of space where we have defined prior calculations. That's really why I want to be careful here and stick only with functions that I already know how to handle. Okay, so what I'm about to do is erase all of this. We are going to take this function now. It has a funny name. It's written as the gradient of f, but if you wanted to, you could just replace that with the letter g. So it's just a function from Rn to Rn, which we know to be differentiable because f is twice differentiable. I'm going to take this expression. I'll expand it in coordinates so that we can really see what computing its Jacobian matrix would look like. And then we will proceed. And we'll have the Hessian matrix. We'll make some observations about it before we move on to an example. All right, let's get going. So what we can think of as d of df, say evaluating that second order differentiation at p, this can be written as d squared. I'll give you the more common expression at the end. We are going to evaluate this by doing the Jacobian of the gradient of f at p, and then we're going to transpose that. Okay, let me now expand this in coordinates. So what does the gradient of f at p look like? Maybe I should be careful here because I want to make sure that I don't plug in specific values before I've done the active differentiation, because you don't want to say you're differentiating constants. So let me say that this is the gradient of f, which I'm about to write down in coordinates. And we'll save the evaluation at p for the very end. So this is like f sub x1. Done in generality, second coordinate is f sub x2, or df dx2, all the way through the derivative of the scalar value function with respect to the nth input. There are so many subscripts in this lesson, by the way, that I'm probably going to make mistakes with my subscripts more than once. Okay, so we want to do that, transpose it, and then plug in p. So basically, it's like don't evaluate anything until you're done taking derivatives. Okay, I've written this as a row in the usual way to save space, but when I write parentheses and commas, I mean an n tuple, and that's something that you should think of as a vector in Rn. So if I wanted to write this as an array, it would actually be an n by 1 column. So that's a vector in Rn. That's the kind of dimensional distinction that we were making a moment ago. Okay, I have to transpose this after I'm done differentiating it, but I'm actually going to do two steps at once. So I'm going to compute the Jacobian of this and transpose it at the same time. Here's how we'll do that. This is the first coordinate function of this gradient of f. So you think of this as the first coordinate. It's like what we would call the first component function. Normally, to compute a Jacobian, you would take this first coordinate function and compute all of its partial derivatives and arrange them along the first row. But since I need to make a transpose, instead of doing two large matrices, I'm just going to do one and say that we are going to take this and differentiate it with respect to each of the inputs, and I'm going to do it in a column. So that's the transposing action at the same time. Let me do this with colors. Watch your subscripts here. I'm bound to make at least one mistake. Take this, and now differentiate it with respect to x1. I'm going to do three things at once. I'm going to go ahead now and say we've done the end of the derivative for this coordinate. Let's plug in p. Okay, so three things are happening right now. Stick with this first component function, take its derivative with respect to x2. Once you're done, plug in p. And keep going. Take this first coordinate function, compute its derivative with respect to xn, and then plug in p. Okay, I don't see any subscript mistakes. I think we're good so far. Let's do pink. Oops, sorry. Now I need to take the second coordinate or second component function of this gradient and compute all of its partial derivatives. Again, in a normal Jacobian, you would take the coordinate functions and compute their partial derivatives and arrange that along a row. Since we're transposing, I'm going to do it in a column. So take this, differentiate it with respect to x1, plug in p. Then with respect to x2, and keep going until you finish. Okay, so these went here, and these went here. All right, continue. I think you're probably with me, but let's just pause for a second and see if you can finish this matrix. So write the final column. All right, I hope you understood what to do because I'm about to write this column in blue, and blue is the hardest to see. I'm just out of colors at this point. So to get the final column of this matrix, we're going to take this component function and differentiate it with respect to each of the n inputs. So that would look like f sub xn, that differentiated with respect to x1, and then it's safe to plug in p. Second row, last entry will be df dxn, compute that, and then differentiate that with respect to x2. And then f sub xn xn, oops. I was like, I'm on the last entry and I didn't make a single mistake. Okay, let's fix that. F sub xn xn at p, that is the bottom right entry. Okay, let's just verify. This is all the component function df dx1, differentiated with respect to x1, then x2, then xn, df dx2, differentiated with respect to each of the n inputs, df dxn, again, differentiated with respect to x1, x2, all the way through xn. This object is what we will call the Hessian matrix, and we can denote that as HF. Here, we've computed it at P. It's like the Jacobian matrix, it's the next level. Okay, I want to make a few observations about this matrix, but I think that it's something I would like for you to do first. So pause, look at this object. Hopefully you have it written down on your own paper in front of you, especially in case any of my subscripts are hard to read. Say as much as you can about it. So just what are all of the observations that you would expect me to make? Maybe there aren't that many, maybe just one or two things to say, but let's do it. So make every observation about this Hessian matrix that you can. All right, let's see what you were able to come up with. I would say the first thing that you should note to yourself whenever you meet a new object like this is the dimensions. So this has n rows and n columns. It's an n by n matrix. Okay, that's one thing to note. What if F were C2? So imagine that each of the entries in this matrix was a continuous piece. At this point, actually, let me back up. We've evaluated each of the components at P. So if you have a point P where you've computed this, then this is a matrix of numbers. But say that when I took all of the derivatives before I plugged in P, each of the expressions that we wrote down that we then plugged P into, imagine that each of those pieces was continuous. Okay, so that's my long-winded way of saying imagine F is class C2 on A. What could you then say about this matrix? And you might want to think back to that theorem I mentioned when we opened this lesson. Well, if you look, say here and here, we have df dx1 differentiated with respect to x2. Here we have df dx2 differentiated with respect to x1. If f is C2, which it will be in practice for us in this class, then these two are the same because order doesn't matter thanks to Clairaut's theorem. So let me say if f is C2 on A, this matrix is what we call symmetric. It's equal to its own transpose because if you swap entries which are symmetric across the main diagonal, you don't change them. So this would be a symmetric matrix. Let's see. I think there's one more thing I want to say, and that is that if I ignore that symmetry and really stick to the Hessian as I've written it here, H sub ij, so the entry in the Hessian matrix in the ith row jth column, so the ijth entry in this matrix, be careful with the order. It's actually F sub xj xi. So if you look at the entry in the second row nth column, it's F sub xn x2, so like 2n n2. Of course, with the Clairaut's theorem, you could say it's F sub xi xj. And typically that would be the case. Typically, if we're looking at a nice function, we would conclude that it was C2 and we would have a symmetric matrix. But I want to mention this because we'll see this form again in just a few minutes. Let me say that I have seen pages on the internet where the Hessian was written as its transpose. So if we'd taken this component function and differentiated it along the row, we would have done the transpose of this matrix. That is technically not correct. So this is the correct form of the Hessian. If you are looking at a different source and it's written with all of these subscripts flipped, then they have taken the transpose. It's probably safe because they're probably working with C2 functions for which this matrix is symmetric, but technically it's not right. By the way, also be careful if you're reading it and it's in Leibniz notation, actually the order would look right. So this would be dxi dxj. So it's also possible that you're looking at a site where it's written like this and it seems backwards, but is correct. Okay, what I would like for us to do now is just take a very nice, simple function. It's going to be a scalar valued function of two variables, x and y. We will just compute the Hessian. There's no trick. It's going to have nice component functions. And we will just observe that it's a nice symmetric 2x2 matrix. Then we will go back into theory. So we've done a lot of theory. Let's take a break, just do a computation, back into theory. I went to talk about what this acts on because it is a matrix. So you want to think of a matrix as being associated to some kind of map. So what kind of map is this? It might surprise you. And we will give a little bit more detail about the Hessian. As promised, here is a scalar value function of two variables. We are going to compute the Hessian matrix in general. So at any point x comma y, and then we'll plug in how about 1, 0. Okay, the first thing I'm going to do is write down the gradient. You could write down the Jacobian if you want, but I just like working with the gradient. It's the same entries, just as a vector. Okay, differentiate x cubed with respect to x, we get 3x squared. Differentiate xy squared with respect to x, and we get y squared. Sine of x with respect to x, we get cosine of x. And then y to the fourth with respect to x, we get nothing. For the second entry in the gradient, we are going to differentiate x cubed with respect to y, we get nothing. Xy squared with respect to y, we get 2xy. Then sine of x, that's going to vanish after differentiation with respect to y, plus 4y cubed. Okay, so here's our gradient. What I'm going to do is take this first component function and compute its partial derivatives with respect to x and y and store those in a column. So we'll say that the Hessian matrix evaluated at any choice of point in the domain R2 has a first column which looks like 6x. Do this in colors again. So how about 6x plus 0 minus sine of x? Now differentiate this with respect to y, and we get 2y. Okay? Coming along now to the second coordinate function, take its partial derivative with respect to x and y, and that will form the second column in our Hessian matrix. With respect to y, we get 2x. And then with, nope, sorry, did that wrong. With respect to x, take the second coordinate function, differentiate it with respect to x and y. So first with respect to x, we get 2y. And then with respect to y, we get 2x plus 12y squared. Like so. Not too exciting. It's 2 by 2. So f is a scalar-valued function of two variables. If it's twice differentiable, you expect the Hessian to be 2 by 2. It's always going to be square for the scalar-valued function. It's symmetric. So the main diagonal, you don't look at that for symmetry. You look at objects reflected across the main diagonal. So the 1, 2 entry versus the 2, 1 entry, those are the same. If I wanted to now evaluate the Hessian at the point 1, 0 is what I think I said we should do. This is kind of like that point P, or it is that point P that I was using in the derivation where I kept saying once you've plugged in P, it's going to turn into a matrix of numbers. So let's see, if I plug in 1 and 1, we get 6 minus sine of 1. 2 times 0 is 0, 2 times 0 is 0, and then we get 12 plus, no, 2 times 1 is 2, plus 12 times 0 squared is 2. Okay, so this is like the Hessian in general at any point in the domain, and this is what it would look like once you pick a specific point. Okay. I think now that we are ready to go back to our discussion of theory, now that we've taken a quick break just to crank out some specific derivatives. What I want to do is talk about what the Hessian would act on. Before I do that, though, let me actually address this issue of what if f were not scalar valued, but it was actually vector valued. So let me kind of return to that question in just a second. I'll let you finish writing this down first in case you're still doing that. So I've really emphasized in today's lesson that we are working with scalar valued functions of n variables, not vector valued functions like we have in the past. So when we look at second order differentiation, we are only going to do that in real analysis too with scalar valued functions of n variables, functions from say Rn to R, which are twice differentiable. When we have such a function, the Jacobian matrix is really just a row. It's 1 by n. From that, we get an n by n matrix, the Hessian matrix that we associate with the second order differentiation. So you might wonder, is there a Hessian for a vector valued function? What if f was twice differentiable as a map from Rn to Rm? Can we write down a Hessian, something analogous to the Hessian matrix that we've now seen in this lesson? And the answer is yes, but it's not going to be a matrix like you may have seen before. So in particular, if you have a differentiable function from Rn to Rm, the Jacobian is an actual matrix. It's an m by n matrix. Where do you go from there? So from a row, we went to a matrix, and now we're going to start with a matrix. What would happen? And it's something that's nice to think through. I usually find that, when I have students in the room, they kind of come up with this on their own. It's going to be what's going to look like a matrix or an array of matrices. That's something that you can call a tensor. It's not something that we're going to continue talking about in this particular class, Real Analysis 2, but it does exist. So it's not like a normal matrix. Again, it's like an array of matrices. That can also lead you to conclude that we are not going to do a third round of differentiation. So we have the Jacobian, we have the Hessian, and there we will stop, because if we tried to keep going, we would run into a similar issue. Okay, so the Hessian for a scalar valued function is an n by n matrix. Assuming our function is C2, it's an n by n symmetric matrix. What does it act on? That's the next question we're going to answer. So we said that the Jacobian matrix was a linear transformation. It acts on vectors. Is the same thing true for a Hessian? The answer is no, but let me step aside for a moment, get ready, and we will look at a little bit more theory before we wrap up this lesson. To see what the Hessian acts on, let's actually start by revisiting what the Jacobian acts on. So assume f is twice differentiable on the open set A. It's a map from A to R, it's scalar valued. If I take the Jacobian of f evaluated at some point P in A, that's a linear transformation. It acts on something. Let me say it's going to act on a unit vector, which I will call v hat. So in this demonstration, anytime I write hat, it's a unit vector. This is a linear transformation acting on this vector. What does that do? What I'm about to write is an equality, but it's usually written the other way because often we say that this is a nice convenient way to evaluate the directional derivative of f at P in the direction of this unit vector v. So normally we say, hey, look, if you want to do this directional derivative, all you have to do is this matrix product. But I like this because we're returning to the idea that the Jacobian matrix, it's not just a matrix, it's associated to the action of a linear transformation. And now we can give meaning to that linear transformation. So if you think about famous linear transformations, they can be things like rotation, reflection, projection, actions that you can describe in words. Here, if I wanted to describe in words what the action of the linear transformation associated to a Jacobian matrix is, it's the directional derivative of f. In other words, it's measuring how f would change in the direction of v. So to act on this unit vector v with this linear transformation is to say, well, what would f do if I moved in the direction of v? If this directional derivative, it's going to be a scalar value. If it's the number 4, then that tells me that if I take a little step in the direction of v, I would expect or estimate f to increase by about 4 times the size of that step. So that's the meaning behind this mapping here. So it's, linear transformation acts on v, so what? It does something. It computes the directional derivative. So the first order differential operator computes one directional derivative. It makes a lot of sense to now look at, say, 2 directional derivatives, meaning what if I try to do iterated directional derivatives? Let me write it down, then we'll talk through it, give it some meaning. Let's say, again, that we're going to do the directional derivative of f at some point P in the domain A in the direction of v. This is a rate of change. Again, it's telling us the rate of change of f in the direction of v. That's a measurement in its own right. How does that measurement change if I then move in the direction of u? So that's like an iterated directional derivative. I'm going to now set aside that interpretation in words like changing and moving and just do some algebra. But at the end, I'm actually going to go back to what does this mean? And I will put up a movie trying to illustrate this idea of measuring how a rate of change changes as we move in a particular direction. So I'll try to illustrate that with a movie I made in MATLAB. Okay, so let's just do some algebra. This is really inside here. So I'm doing this and saying, this is a rate of change. It's a measurement in its own right. How is that changing? Well, first, just look at what it is. It's exactly what we wrote on the line above. So if I want to simplify this, we can say the directional derivative of f at P in the direction of v. Let me kind of separate it, so I'll put it in parentheses. It's df at P times the unit vector P. So it's this row times this column, giving us a scalar. So keep in mind, this is a scalar. All right. It's differentiable because f is twice differentiable, so I can keep going. And what I now want to do is recognize that I'm taking the directional derivative of a scalar quantity in the direction of u. Just imagine that this was like the word g. you would say, well, what is the directional derivative of g in the direction of u? It's the Jacobian of g times u. So let's write that down, and then I'll do a little manipulation with that. So kind of formally using this way of rewriting a directional derivative, we're going to say that this is the total derivative of this expression times u, times the unit vector u. Okay, so again, from here to here, it seems like there's a lot more going on, but it's really just another version of this first equality. Okay, this quantity inside here is, again, a scalar. You can work out what this is as it's written in coordinates, do its directional, or do its total derivative as Jacobian. I'm actually going to do a little bit of a trick so that I don't have to pass into coordinates. And that is, I can take this scalar and transpose it and not change it. So if I formally transpose this product, it doesn't affect the equality because the transpose of a scalar is a scalar. But when I transpose a matrix product, I can use the fact that, if you have two matrices, A times B, and transpose it, it's B transpose A transpose. Okay, so this is a row matrix, this is a column, I'm going to transpose them. The original vector V now turns into a row, and the transpose of the Jacobian of f at P is the gradient of f at P. And I like doing that because it's clearer to me how to now compute the total derivative of this expression. This is a product. This is a constant. I didn't really say here what u and v were. Sorry, my apologies. U and v are just any unit vectors. So maybe I said that for v up here, but I'm imagining here that u and v are both just unit vectors. So v is a fixed unit vector, u is a fixed unit vector. So if I want to differentiate this product, it really just amounts to differentiating this gradient. We already said that's totally safe. You can do that. That's the kind of expression that we happily work with. So if I now do that, this constant stays out front. The derivative of the gradient of f, or rather the Jacobian of the gradient of f, is the transpose of our now familiar Hessian. So let me write hf at p transposed times this unit vector u. Let's add dimensions. So this is like a triple product here, and I just want to make sure everything checks out and also recognize what the result of it is. V hat was a unit vector. When I transpose it, it turns into a row. So this is 1 by n. The Hessian is n by n, so its transpose is also n by n. And then u hat is another unit length vector in Rn, so that's n by 1. The result of this matrix product is a scalar. So it's 1 cross, 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 cross by 1. Okay. That means, once again, I can just take a transpose. I'm allowed to just do that because it's a scalar. So if I transpose this whole thing, we preserve equality. And it's going to be this unit vector u transposed, so that's going to come over here. The transpose of the Hessian, flip, flip, you get back the original Hessian. And then the transpose of v, you get back v. Let me pause here because I went through this kind of quickly, so let me give you a chance to make sure you've got it all written down. Check my algebra on each step. I think it works out. And then we will come back and say what this line is really telling us. To summarize what we have now done, because we've actually reached a conclusion here. When you do the first order derivative, when you compute the Jacobian matrix or the total derivative of a function, you produce a linear transformation. So the Jacobian matrix is the matrix associated to a linear transformation that acts on one vector at a time. What we established here is that when you act on a unit vector with your linear transformation, you can actually give a meaning to that. It's one round of a directional derivative, meaning you just do a basic directional derivative. So we compute the rate of change of f at p in the direction of the unit vector v whenever we act on that unit vector with our associated first order linear transformation. To go to the second round of differentiation, it makes sense to say, well, what happens if we were to do two layers of directional derivative? So that's what we did here with this iterated computation. And what we actually have produced at the end is called a bilinear form computation. So let me say that again. This interior matrix here, this n by n Hessian matrix, in this matrix triple product, this is describing the action of a bilinear form. So the Hessian matrix here is a bilinear form. It's linear with respect to the two vectors it acts on. So bilinear form acts on two vectors. Here, we're acting on the pair of vectors u hat and v hat. And the action of this bilinear form, like how do you act with this operator on this pair of vectors? You do this matrix product. So HF at P acting on this pair of vectors, to evaluate that, you would do U transpose the Hessian times V. A little thought experiment. If I did do a third round of differentiation, so I said we wrote down the Jacobian, we wrote down the Hessian, we won't keep going, but imagine that we did. Say I wrote down an operator I said was the third order total derivative, so the Jacobian of the Hessian. What would it act on? So can you kind of deduce how we would describe it? What would be the sentence we would write here? Well, if I had the next round, it would be a trilinear form acting on a triple of vectors. Now, what would that look like? It would be a little bit complicated because, again, we would have like a tensor, so we'd have to define a product that would involve three vectors kind of from different sides. So I just want to mention that, though, because now you can kind of extrapolate what each layer would do if you kept differentiating. If you did it 4 times, if you had some sort of fourth order differential operator, that would be quadrilinear form acting on a quartet of vectors. So this is the natural environment for the Hessian. While it is a matrix, and to any matrix, you can write down a linear transformation. So I could take this Hessian, it's a matrix. I can just multiply it by a vector, but that doesn't really encode what it naturally does. That doesn't give us any sense of meaning. This Hessian naturally lives inside of this matrix triple product. It is a bilinear form. It only really makes sense to think of it as an operator that acts on pairs of vectors. Before I pass to my movie illustrating what this idea of like two directional derivatives is, let me reiterate here that this makes sense. And in fact, it returns us back the coordinates of the Hessian. So take a moment on your own. Let me give you an exercise and I'll come back and solve it. What if I acted on the vectors EI, EJ? So this is a question for you to work out for a couple minutes. What is the Hessian matrix acting on the pair of standard basis vectors given by the ith standard basis vector and the jth? Okay, so see if you can compute that. And if you do it correctly, it should remind you of something that we've already written down today. Okay, so let's see what you got. If I take this Hessian matrix and act on this pair of standard basis vectors, using this expression, I'm going to say, all right, it's EI transposed. So that's a row of zeros except for a 1 in the ith coordinate. And then the Hessian matrix times the jth standard basis vector. Okay, I'm going to do this out loud. If you take any matrix and multiply it by the jth standard basis vector, you extract the jth column. So the result of this product is the jth column of the Hessian matrix. When I multiply that from the left by this 0, 0, 0, 1, 0, 0, 0, this ith standard basis vector, what we're going to do is zero out every coordinate from the jth column except for the ith one. So that's going to be the ith row and the jth column. Everything else vanishes. In other words, it's what we called earlier H sub ij. Let me mention before I connect that to something we wrote down a minute ago that these are unit vectors, but this matrix triple product works for any pair of vectors. So if I wanted to say, how does the Hessian act on two random vectors from Rn which are not unit length, you can write down this product. What's nice about writing down this product when they are unit vectors is that you can also then come over here and do these directional derivatives. So what would it look like if I did this side of the equality? We did this side, let's do this side. That would be d sub ei d sub ej of hf, sorry, no, f at p. But a directional derivative in the direction of a standard basis vector is really a partial derivative. So this is the partial derivative of f with respect to the jth coordinate. So I'm really filling up this board, but don't want to erase anything quite yet. So this is f sub ej, or let me say xj. And again, we're doing a directional derivative of an expression in the direction of a coordinate vector, standard basis vector, so that's another partial derivative. So this is going to be this expression differentiated with respect to xi. Okay, again, sorry about like really splitting this computation up over here. So let me kind of distinguish what we've got. All right, we're now saying if we've done this formula correctly, the ijth coordinate of the Hessian matrix is f sub xj xi, the backwards order, that second order partial derivative. And that is actually something that we already associated or already established when we computed the Hessian matrix. So we just kind of got to it two different ways. Okay, there's a lot going on here. Let me give you a moment. Maybe you got all this, but didn't make this association. So take a moment to work through that computation. And you might want to flip back in your notes and see that we'd actually already written down that h sub ij is this second order partial derivative. When I come back, I'm going to probably erase all of this and I'll put up and talk through a movie just illustrating this idea of a double directional derivative. So to the Jacobian matrix, we associate a directional derivative. To the Hessian matrix, we can associate this idea of a double directional derivative. That's something you might be struggling to picture. So I'll give you a graphic. It's kind of an exaggerated illustration of what that computation is measuring. As promised, here is a movie illustrating in a very exaggerated way what the geometric measurement of a double directional derivative is. So in particular here, I'm actually not giving any random double directional derivative. This is specifically dE1, dE2 of some function of two variables at some point in its domain. It's very exaggerated. Differential calculation is a very local action, so you compute instantaneous rates of change whenever you're talking about derivatives. Here I'm kind of stretching a behavior out over the domain, but that's just so that you can really see what's happening. So imagine we're at some fixed point AB. Well, what is this? Let me write it down here. This is f sub y sub x. So to the right here, it's not just a random double directional derivative. It's actually this mixed partial derivative that I'm trying to illustrate, but that's just one special case of having a double directional derivative. Okay, what's happening here is that each of the red line segments at the points where I'm sketching them is a computation of the form df dy. It's trying to illustrate this concept. So if you look, it's like each of those red line segments is happening in an x equals constant plane, and I'm showing the slope of the tangent line in that plane, or in other words, how f changes with respect to y. So each of those little red segments is measuring the sensitivity of f with respect to the y coordinate, and again, I'm stretching it out over several points. That I'm stretching it out over several points is me trying to illustrate how that slope changes as a function of x. So the lines, this progression of slope values that we're seeing is happening in the x direction. So it's like, how is df dy changing as you perturb in the x coordinate? So that's what I'm trying to illustrate here. So it's like this idea of kind of bending is a second order differential measurement. It's analogous to concavity when you look at functions of the form y equals f of x. Sorry about overusing x, y, and f in this demonstration. when you have a function which is concave up, say the second derivative of f is positive at a point, what you're really saying is like, how do the tangent lines change? Now, these tangent lines I'm sketching left to right. Whoa, got really steep there. Started negative, but that's not really what you're measuring with the second derivative. It became less negative, zeroed out, turned positive. It was an increasing function. So it's like the slope of the tangent lines was increasing as I traveled left to right. And that is this idea of a second derivative measurement. So how is the first derivative changing as a function in its own right? Now, when you mix directions, it might be harder to sketch, but it's really the same idea. So we're measuring how a rate of change changes in a direction. Okay, so I hope that helped clarify what this idea of an iterated directional derivative is computing. And I hope that you enjoyed this lesson on the Hessian matrix. I think it's kind of a fun operator to work through. We are going to use it though. So yes, the Hessian's interesting in its own right, but we are going to do Taylor series or Taylor approximations of functions. And for that, we will look at writing down something which is analogous to what you might have called in a calculus class the second order Taylor polynomial. For that, we will need the Hessian. So that will emerge in our Taylor series computations, which we will do in upcoming lectures.